Okay, good morning. Last day today. So I did not prepare well my lecture today. I was too tired. I slept long, so I had no time to prepare. So don't worry if it is a little bit, let's say. All right. So I just recall here what I did in the last lectures. I was looking to the effect of the acceleration of the flame to the transition, for the effect on the transition, on the DDT. So the mechanism was the following. When the flame accelerates, maybe I should remember what kind of situation I am looking at. It is I consider this tip of the flame pushed from behind by the backflow here as a planar flame. This is one of the first approximation I did that I will explain. I will explain in details later on. So it's a planar flame. As you see, when this planar flame acts like a semi-transparent piston, so it push when it moves, it push the gas ahead, and when it accelerates, this like a piston. When a piston accelerates, it sends acoustic wave of compressible wave in front of the flame. And this compressible wave warm up, you know, as the mixture because of the compression effect, and this react on the flame velocity. So this is a loop that is going to produce the DDT. So okay. So I found, taking into account the compressible effect in front, unsteady compressible effect in front of the flame, I found out a similar situation as the self-similar solution that describe a flame propagating at constant velocity with a lead shock ahead propagating also at constant velocity. This and when you change for different backflow, when the backflow increase, for different value of the backflow, the solution, which is quasi-steady, this solution quasi-steady has a turning point. It turns out that when you take into account the unsteady effect, compressible effect in front of the flame, of an accelerating flame, you find the same type of turning point. That is, above a certain velocity of the flame, which is related to the velocity of the backflow, the intensity of the backflow. Below, above this critical value, there is no more solution. Even there is no more unsteady solution. So the question is now, what is going to happen at this point? As I recall briefly, now what I said the last time, is that it is easy to show that near this point, it turns out that when the flame is going when the backflow is going to reach this critical value, the flame velocity approach this critical velocity, And it is clear that in that, at that moment, the flame acceleration diverge. It diverge, you know, the velocity approach the critical velocity here, like a square root of t star minus t, where t star is the time at which we arrive at this value of the elongation, or the backflow, because the backflow is proportional to the elongation of the finger flame. So now, because you approach the critical velocity as a square root of the time, this is due to the fact that that this turning point is a maximum of sigma versus uf. So, you have such relation. It is a quadratic relation. And then when you inverse that to have the flow velocity in terms of the time, you have the square root. So when you have, for a constant rate of increase of the elongation, so that this elongation is like the time, for this is you approach as a square root the critical velocity. Now, if you take the derivative of that, you by derivation you obtain that the acceleration of the flame is going to diverge, becomes infinite at this moment. So you are expecting a drastic effect, because when you are studying compressible phenomena, and then you have an acceleration that diverges, you are expecting a drastic phenomena. And a first indication is now this equation was for the flame speed, uf, in terms of the elongation in terms of time. Sigma is like the time here. Now, what is interesting to study is what about the flow? So yes. Now, what about the flow here? You see how the flow is behaving. And this can be computed. This flow can be computed using the Riemann. That is a very old work by Riemann. He gave to you the equation of the flow, and this equation of this flow, this is a compressible flow. Okay, it is like what is called a Burger's equation. That is, the time derivative involves a square term, which is u du over dx. This is the nonlinearity that is associated, that is associated with the compressible effect. And this Burger equation has a solution. Here is the solution, that the flow velocity divided by its critical value here approach the critical value like a square. So it is a field now. It depends on x, okay, to be sure that everybody understands. X is in that direction, right? So this flow is a field. So it's a function of distance from the piston and time. It behaves like the square root of, like here, t minus 1, but plus x minus xf is the position of the flame, and x minus xf, capital XF, is the distance from the flame. So here you are. This is the solution of this Burger equation. And now if you take the gradient of the flow, you take just d over d, the derivative of u with respect to space, okay, which is here. You have 1 over square root of something of these things. And now if you look to what happens to the flow on the flame, that is x equal xf is 0, you obtain something similar to the acceleration, that you obtain a divergence when you reach this point of the gradient. So the flow, the gradient of the flow is going to diverge on the flame. And this, you know, you can anticipate that this is the onset of a shock in the flame structure. And the question is, does this is a mechanism of DDT? This is a question that I want to address now. Okay, okay, we can skip this. This is a formulation, I can skip that. Okay, let me check, okay. No, but I don't enter into the detail now. So I was looking now, maybe I should have to explain that in more detail. No. Where are we? Okay, beyond self-similarity, all right. Finite time anxiety of the acceleration, all right. Now, what I am going to do is to take into account now the unsteady effect. You know, for the moment, I have described the unsteady effect in the compressible flow ahead of the flame. But to go further, I will take into account the unsteady effects that you have in the burn gases, that is here, compressible. The unsteady effect here, you know, when the shape, when the length of the fingers increase with the time, you have an unsteady flow here. So up to now, I assume a quasi-steady state of this flow, slaved by the length, but there is a response of that. You know, the length, if the length increases, the flow does not react immediately. He has a delay to react. And I want to take into account this delay to see how the solution is disturbed by this delay. This is what I am going to do here. I will not tell you the details of the analysis. Okay. There are two. I am confusing myself. Excuse me. This is the inner structure plus inner structure quasi-steady. Delay by flow. Okay. Now, what I did yesterday, I was looking to the response of the burned gas to the unsteady length of the finger flame. And finally, I showed the following, is that if the quasi-steady is a flame, if you neglect the unsteady effect, you have this equation without the yellow part here, which is, you know, this, excuse me, this is simply the elongation. The elongation is proportional to time, tau 1 here, which is not exactly the time, but it's a time scale in a proper way. And P1F is also the pressure on the flame scale also in the proper way. So this equation that I have obtained, assuming that the burned gas is in steady state and that the inner structure of the flame is in a steady state, but taking into account the unsteady effect in the fresh mixture, is this transcendental equation that presents the turning point. Now, the effect, the delay introduced by the response of the flow to the change of elongation introduce a derivative in the equation here of the unknown, which is here pi 1 f, which means the pressure on the flame. So here is the equation, okay? This is well expressed. It is written here differently. I have put on the right the derivative of the pressure. I have introduced a non-dimensional, a reduced pressure nu here, you know, which is the pressure times a coefficient, that is a constant, which is associated with the activation energy, in fact, reduced, and this is offer the unity, this B is offer the unity. And you see this exponential here is this one, because I divide this equation by this term here, which is exponential minus nu. So in that case, here you have this is psi, which is here, which is the time, if you like. It's like a time. It's elongation, reduced elongation, which is here. I have now. You have here this this quantity here. Nu is unknown, multiplied by the inverse of this quantity, and on the right, you have divided by that. You have just the derivative of the pressure. So this is the same equation as before, written in a more convenient way, expressing the derivative of the solution in terms of the time, because Xi is like the time, elongation is like the time. And what you have on the left-hand side, if it is zero, it is a quasi-steady, it is a turning point that I have described. It represents the solution of the turning point in black. So the left-hand side here equals 0 is in black. Now, you want to see what is the effect of the this term is small. I have used a small perturbation analysis to take into account this the unsteady effect in the burn gas. And to begin with, I assume that this unsteady effect is small. That this is as usual in every analysis. So this is the small, the fact it is small, it is multiplied by this epsilon, which is related to the Mach number of the flame, laminar Mach number of the flame. I have assumed this. So now here is the equation written. Okay. Now, if you develop around this point, as I did before in the quasi-steady state, this is the same equation that I had before. And now on the right-hand side, I have simply the derivative with a small term, which is non-dimensional, written in the non-dimensional way here. And it turns out that I have explained to you that this equation you know, if you replace y nu star minus nu by y, nu minus nu star by y, and you replace this elongation by t, when you reduce everything, you have an equation of the type dy over dt here, h is equal to t here, plus y square, y to the y to the square. So as I told you, this equation, sometimes this equation is called in different way, but it's a when you neglect t, this equation is well known and can be integrated easily, as I showed to you, because you divide by, forget about the t for the one. Assume that y is going to infinity, which will be shown in detail. But assume it is, so forget about this term. And this equation, when you integrate, you divide by y squared. On the left-hand side, you have the derivative of 1 over y. And on the right-hand side, dt give you t. Now, this is going to give you something like t star minus t, y equal, and so this is 1 over y, so that y is going to be proportional to the inverse of t star, tc is a critical, it is associated to this, that this one has to be computed by the initial condition. This is not so simple. It's an interesting mathematical problem that can be found. In fact, the reference of this problem can be found in this paper, which is a recent paper, not recent, but not very old. So it's clear that now the solution is quite different from the quasi-steady solution. Why? In the quasi-steady solution, there is no solution above the critical value here, elongation. So you don't know, but there is no divergence of the solution. So here is the pressure. Here, there is no divergence of the pressure. Now, as soon as you add a small, take into account a small derivative term, here it's no more, it is no longer small because I have scaled everything in such a way the t is absorbed, the epsilon here is, excuse me, the epsilon here is absorbed in the t. So you have, you turns out that a small disturbance indeed changed drastically the solution. And here in black, you have the quasi-steady solution. In red, this is the solution including the small unsteady term. And you see it is drastic because now the solution nu diverge at a finite time just for a time a little bit larger than the critical time. This is a mathematical result that can be understood clearly. You say, okay, if I go to infinity here, I can, and I am still at finite time, I can forget about this, and this is explain you why it diverges. So this, the solution of that is of this type, 1 over Tc minus T. So you can understand simply by this simple model how a small disturbance, a small derivative term changed drastically the solution. Now, what is even clear is that smaller is epsilon tilde here. Smaller is the distance between this critical, the two critical value. One is a quasi-steady critical value, and this is an unsteady critical value. So, as I told you, this is a generic equation. This is called in mathematics dynamical saddle node bifurcation. You know, to make you understand what does mean this vocabulary, you know, what is a saddle node? You know, for a constant, for a given time, you have two solutions. This one, excuse me, and this one. Now, it turns out that according to the trajectory in the phase space, this is stable and this is unstable. So, in a sense, you see that this is a node and this is a saddle. And this saddle node, this saddle and the node, the two solutions collapse. And so when it collapses, you run away, you got a divergence in the solution. So this is recall in yellow. This tells you that the pressure is diverging. But you know, when the pressure is diverging, you cannot, you know, it is clear that the analysis based on a quasi-steady flame does not work any longer because the pressure is diverging. So, but it tells you that the inner structure of the flame is going to be blown up in finite time by the divergence of the pressure. And the slower is the elongation rate, that is smaller is this coefficient. The close to the critical time is the lower. That the close to this quasi-steady state critical elongation, the dynamical one get closer and closer and closer. In such a way that if you go to zero, for example, now you know this is subtleties of distinguished limit. Now, if you go to zero, what is going to happen? This critical dynamical critical value of the time is approaching the quasi-steady critical solution. So this in this case, this solution is going to be like that. Now, the important thing is that the difference, the essential difference, is that now the solution is no longer bounded, is unbounded. So it is a divergence at finite time. This is catastrophic. Detail, I don't care. Now, something was missing in my analysis. I did not take into account the modification of the inner flame structure for the moment. I just take into account unsteady compressible effect in front of the flame, unsteady effect in the burn gas, take into account, but I did not take into account unsteady effect inside the flame for the moment. And this cannot be right. Why? Because the acceleration of the flame is going to be very large. So if its acceleration of a flame is going to be large, clearly the flame structure is going to evolve, to change with, it cannot stay steady. So this is the last part of the analysis is now to take into account the unsteady effects inside the flame structure when the acceleration of the flame increases. All right? This, in fact, I will show you. This is difficult. It's difficult to understand, and the result is going to be. It is a very strange result. That maybe I will explain that in future. Before I skip that, and I can. This is a limitation. I will be back. And where I no. So it is not here. Okay, forget. I thought it was it was written here. It should have been written here. Where is it? I don't want to give you the detail of the analysis. Limitation, no. Okay. I don't know why it is written like that, maybe, okay. The problem is, when you look to the unsteady effect inside the flame, there is a problem which is related to that. It's, in fact, what about the stability of this branch of solution when you take into account unsteady effects inside the flame structure? This is a key problem that can be solved analytically. I did that a long time ago when you look to the response of the flame to a pressure fluctuation. For example, how the flame structures react to a pressure fluctuation, for example. This has been performed. I did that a long time ago in 1990. And now what you do, the problem is the following. You consider a fixed elongation, and you look to what is going to be the response of the solution, steady, when you put a fluctuation of the pressure. How does it work? And that is if it turns out to be unstable. What does that mean? That if you look to a solution in the form exponential the times a space function, you are going to find, when you look to the unsteady analysis to this problem, that the real part of this of the growth rate is positive. So, following an analysis that I have performed a long time ago, this solution, if you neglect unsteady effect ahead, unsteady effect behind, and keeps only the unsteady effect of the inner flame structure, it shows you that this branch is unstable. This is a disaster. Because if the flame is unstable, what is the utility to work around this turning point? Because you start from somewhere, but if it is unstable, you do not follow this thing. Hopefully, it turns out that this instability, the growth rate due to this inner instability of the flame, is counterbalanced by the unsteady effect in the burned gases. This is why I say that in the previous slide. I said that, unsteady inner structure of the flame, see a few slides below, that does not change the result. when I did this analysis 2 years ago, I was scared. I said, my goodness, all my work is going to be destroyed by this result, by this instability. It turns out, when you look carefully to the problem, that when you have such a relation linking along the size of the finger divided by the flame thickness, laminar flame thickness, it is larger than this term here, where epsilon is small. So it is a large number. So when you are above, let's say in simple words, if the size, the length of the finger is longer, sufficiently longer, the unsteady effect in the burn gas balance the bad unsteady effect that I have coming from the inner structure. And in that case, nothing is changed, but you have to be, you need to have a length of the finger sufficiently long. And this, it turns out that the length, the characteristic length that you have here is not longer than it is, that this is true already at this point. So finally, the result stay the same as excuse me, it was before I take into account the unsteady effect of the flame. So to conclude, I have a simple description of the transition in this problem. Excuse me. Okay. So I have a simple, now looking to a planar flame, which is accelerated by a backflow. This planar, I should have somewhere. Here it is, no? Okay. When you have this backflow here, the flame is accelerated, you take into account the compressible effect. When you take the solution you obtain for the pressure on the flame is that it's going to diverge as soon as the length of the finger is sufficiently long. Everything is stay laminar, but you have a divergence. So now, what can be said more than that? It's clear that this is a pressure diverge. You should expect a detonation. That's because this is only combustion waves that deals with a large pressure jump. So, but one has to be clear that I did not describe exactly the transition. I just show that there should be a transition, but I did not describe exactly how is the transition, because I did not take into account. I was unable to, and I will explain that in more detail. I am unable to describe the birth of the shock. You have a shock, but I don't know how, and I will give you more details, some comments about that. Because it is important to realize. Okay, now let me be back now to look to the different approximation I did. The first was to consider the tip as a planar flame. So the first thing is to look at what about the curvature here? What will be the effect of the curvature of the inner structure compared to the inner structure of the planar flame? This is easy because the transverse diffusive effect should be of should induce an inverse of the time, which is of the order of the thermal diffusivity divided by the radius square, and this inverse of the time, this time should be smaller than the rate for the inverse of I am tired this morning. It is the this time is the inverse of the transit time of a fluid particle across the flame. So if the flame thickness divided by the radius is smaller than unity, you may, and if you may neglect such small term, in that case you may neglect the modification of the inner flame structure by the curvature. That you can justify the approximation of a planar flame. But now, what you need is this term should be smaller than the compressible effect that you have retained. Why this the analysis is not coherent. So what you need really is, in order to assume that the flame can be considered as planar, is that this ratio square should be smaller than the Mach number. Mach number, I recall you, is the Mach number of the laminar flame, which is the flame velocity laminar divided by the sound speed, which is always small. It's 10 minus 2, 10, something like that. But this, once again, be careful to distinguish clearly the laminar Mach number with the Mach number based on the flame propagation. Why? Because you have this backflow here behind, which is increasing strongly. And as I explained that in detail yesterday, the velocity of the flame here, let's say, the speed of the tip here could be much larger than the laminar flame speed, and even so large that it can be approach the sound speed. So, in a sense, let's say that the Mach number based on the speed of the tip is not small, but the Mach number based on the laminar flame speed, UB or UL, is all the time small. This is don't confuse the things. So this epsilon is here, is the Mach number, you see, of the laminar flame speed, UB or U divided by AU, but you can add UL divided by AU or UB divided by AB. This same order of magnitude. The order of magnitude is 10, between 10 minus 1 and 10 minus 2. So what you need is that the length should be long enough compared to the detonation, to the flame thickness, in order to still consider the flame here as planar. Now, if you look now to the final when you put all the things together, when you consider you have another, you have two. The problem has two small parameters. The one is the Mach number, laminar flow Mach number, laminar flame Mach number, this epsilon here. Another epsilon, I don't know how to spell that, is elongation rate. And if because you are working in a small elongation rate, the analysis, the planar geometry near the tip is valid anytime you have this relation here, saying that the Mach number of the laminar flame velocity is smaller than the elongation rate, which should be also smaller than 1. So in this condition, you verify that the planar approximation at the tip is verified. So this is not okay. Excuse me. Okay. So this is okay. Now, as I told you, the second point, very important point, is the physical branch of the black solid line here, the quasi-steady solution, is it stable? I gave you the answer. This is true if the length, okay, here is a more detailed relation. The length of the finger flame should be sufficiently long in order that the delay introduced in the backflow is sufficiently large and so balance the instability, the natural instability of the flame. So this is in 3 steps, but I will stop. Now there is an even more drastic limitation of the analysis concerns the slow dynamics that I have used. You know, it's clear in a sense that but forget about the detail. Okay. That because of the acceleration, you know, is going to be large and large, it is clear that the dynamics, the overall dynamics is no slow. So as I assume a slow dynamic at the end, I have a problem. It turns out when you look carefully to when the assumption of a slow dynamics breaks, that you are around this point. And so you see, let's say, roughly speaking, this, you see yes, you see where is my finger there? It turns out that it is right up to here. So you prove, the analysis proved to be valid much ahead for a larger time than the critical time. And when the pressure here, this is the pressure, has increased much, not sufficiently above the critical steady state. So now you cannot say that this is true here, because you see the acceleration here is very large, because in very few time you have a very large change in the pressure or in the velocity of or the laminar velocity of the flame. So this does not work here, but it works. The analysis works, let's say, you see around that. And now it is also so the assumption of a slow dynamics is not valid in the final stage of the runaway. However, a finite time singularity is not doubtful. Why? Because when you are here, there is no more quasi-steady state solution. So there is no other possibility different than the singularity in finite time. But this is not a proof. It's not a mathematical proof. But however, you can prove mathematically, with the correct analysis, that the pressure has increased, let's say, for the unity, which is at least. And this is a little bit, you cannot say much than that. Now, here are the conclusions. Okay, the conclusion is that here I can skip that. So there is a catastrophic process and so on. And what is the physical mechanism of this singularity is the nonlinear thermal loop of the compressible effect that increase the temperature so that the laminar flame velocity increase. This acceleration increases the compressible effect, and so you have a loop. And this is this nonlinear thermal loop that is the basic mechanism of the occurrence of this singularity. Okay, this is good, but you would like to have a better insight into the how is built the detonation. That is, you have to create a shock inside the flame structure, and this shock has to be transformed in a detonation. This, as soon as the shock is sufficiently strong, there is no problem. Because if you develop a shock sufficiently strong on the hot side of the flame, the reaction rate is going to increase strongly, and the detonation is going to be built. So this now you have to see that by numerics, see how it works. So this was done by the PhD student Hernandez Sanchez, Raul. He did numerics. What was the numerics? He solved the flame structure. Here is the flame structure, completely solved, and he put it in. He assumed that at the exit of the reaction rate, there is a backflow. And they assume that this backflow follows the law that I have given, that is proportional to the elongation time, the lamina times the phase speed. This is a problem, which is a loop problem again, okay? And then he looked to what is going to be the solution. So here is the result. This is a laminar flame speed. Is a reduced laminar flame velocity, or reduced pressure. It is the same. So during a long time, he is following this. He starts not very far, and start from here. You see, so he stay close. As predicted by this. The departure is not very large, and then suddenly, when you approach, this is a numerics, you have a strong acceleration, diverging acceleration. Here you see the velocity increase in a very reduced time, in very small time. This is the beginning of the singularity at finite time. He saw that numerically, and what he saw is that here is the Chapman-Jouguet velocity detonation of Chapman-Jouguet. The pressure, the velocity of now it is no longer a flame because there is compressible effect inside. The pressure of this in this wave, in this combustion wave, which is above the Chapman-Jouguet, and then back to the Chapman-Jouguet. So the problem is, in this numerics, can we, you know, one problem, what is very interesting from this numerics, that, you know, in order to see a shock, maybe most of you know that, in numerics, there is no other way than to increase the thickness of the shock. The shock is as I told you, is few mean-free paths. So in numerics, when you deal with the macroscopic equation, you have to increase in a proper way the diffusion coefficient at some moment where the gradient diverges in order to see the building of the shock. And this, but what is important is that so you have to disturb the basic model of that you have, the basic equation that you are studying, you have to change when the gradient becomes too strong in order to resolve the divergence. What is very important in this thesis, it is not yet published, apparently. I don't know what he's doing. Maybe he's in postdoc and he has no time to publish that. What is important to say is that up to this point, for example, here, there is nothing that is introduced artificially to resolve shocks. So what is very important is that if the basic equation show clearly the solution that there is a runaway of the pressure. Now, what is less reliable is the following. Because to solve this now, you have to change the basic equation, that you are looking at by introducing, artificial, what is called artificial viscosity. And this is a disaster because you modify completely the nature of the problem. So I do not trust this result here. Let's say I do not trust. No, I think this is going to be interesting. But you know, all the people working with numeric to describe the transition from deflagration to detonation will have this problem. As soon as a shock is going to be created near the flame or at the flame, so now you have to introduce artificial means that can change completely the nature of the problem. And so this is my warning. Be careful to the result obtained by direct numerical simulation on the DDT. For me, I do not trust this result for the reason I gave just to you, that you have to change the nature of the problem. Okay, let's say 15-minute breaks, and I will give you more information concerning this transition by numerics.